Hello everyone, and welcome. Today's presentation is about pre-stress. My name is Flaviu Popescu. I will be your host today. I will be moderating this webinar. I am a civil engineer, a sales and support engineer at StruSoft Denmark. Ciprian Sibea will be helping us today with any technical questions that you have. Please use the questions field in the GoToWebinar platform today. Here is where you can type your questions during the presentation, and Ciprian will try to answer all of the questions you have today. Our special guest today is Senior Engineer Bogdan Buzaianu from Gapa Project Partners in Romania. Bogdan has been a user of pre-stress, and it will be interesting to see how he uses the program for his projects, why he decided to choose pre-stress, and he will talk more about that in the second part of today's showcase. A little bit about StruSoft. We are the main developer and distributor of structural design software in Scandinavia. We will talk about pre-stress today, our tool for calculating and designing pre-stressed concrete beams and hollow cores. Though we have a wide range of products and software. FEM-Design is our 3D modeling, calculation, and design software based on finite element method, where we can basically model and calculate any type of structure in 3D. WinStatic is our single element program for beams, columns, frames. BIM Energy is for calculating and optimizing energy consumption in buildings. Then we have the Impact Suite, Impact Precast, and Impact Reinforcement for factories. Factories who produce prefab elements use Impact for design and management of their production. Today we will be focusing on pre-stress. We have more than 10,000 StruSoft users around the world. We can see here a map of Europe and a little bit of Asia and North Africa. We can see a high concentration of our users in the Scandinavia region, even though we have users around Europe and Northern Africa and Asia. We have offices around the world. Our headquarters is in Sweden, in Malmö, and we have 3 offices in total in Sweden. We have 3 offices in Denmark. Our newest office has been opened in Finland, and we have also branches in the UK, Romania, Hungary, and in Asia in the Philippines, India, and I forgot to mention Estonia in Europe. As I said in the beginning, I will start with the showcase of pre-stress, which is our tool for calculating and designing pre-stress elements. We will present the main and most important features of this program. If you are using it already or have used it, you might be familiar with some of the things that we will discuss today. If you are new to the program, I think you will get an idea of what the program can do. Of course, you would like and you will want to try the program for yourself. So please go to our webpage, StruSoft.com, and apply for a trial there for our software. We provide full technical support for your trial period as well. So we can go and help you figure out how you can use the program for your projects and tasks. After we go through these tasks, through these points, I will hand over the presentation to Bogdan, and he will talk more about his the way he uses pre-stress in his job. All right. You can see the main interface here in pre-stress. I have already loaded an element. It is an eye profile. You can choose from a database of elements, and you can also create your own non-standard profiles. The program is structured so that all the stages from release, storage, up to the final ULS stages are considered. You can also add your own stage at any time or delete stages that you're not interested in. For each of the stage, you can set an exposure class. Bogdan will actually talk about this. He has one of his projects which he has used different exposure classes for different types of situations for his projects. Adjusting pre-stressing force. As you can see, the reinforcement is defined as in this table. You can see the pre-stressing strands, and you can see that there's a default pre-stressing force. You can also simulate non-adherence at the ends of the beams. So you can actually define them according to the x-coordinate into a distance so that the tendon actually starts from within the beam with the amount that you type in here in the x section. So you would actually have 200 millimeters of non-adherence in the ends. This is how you can simulate this non-adherence in the program. It's something that people have been asking about, how you could do this. It's very easy. It's very common and very useful to use. The automatic design of stirrups. You can calculate, you can automatically design the stirrups for your element. The program gives you a mathematical value for these stirrups and a default layout. Of course, it is up to you if you want to go with this layout that the program suggests to you, or you can also adjust it afterwards. What you need to be aware is that the program gives you a mathematical result. So if you have some minimum reinforcement that you need to satisfy in your element, you have to manually adjust it and make sure that it meets the minimum area of reinforcement for your element. I was talking about the non-adherence earlier, and I forgot to mention the pre-stressing force, which it can also adjust. So if you have a default value here for the force, you can, of course, at any time edit that pre-stressing force and change it at any time. You have the possibility to design beams with recess. Let's take a look at a model here. The recess beam is a tool which you can use to design the different types of reinforcement at the end of your beam and make the necessary calculations and verifications. You need to be aware that the supports are taken into account from your model, of course, and you need to satisfy some distancing, some distance conditions. And of course, you have all the fields for the different parameters, and then the different types of bars which you can choose diameter from. You also have different load combinations for which you can do this in the final stages and transport if you consider it. It is possible to define creep and shrinkage in the program and consider it as long-term parameters. This will affect the relaxation and it will be taken into account in long-term calculations. Now, you can actually use our online calculator which is a free app online, which you can use at any time. You specify the properties of the concrete, and you will get a calculation of your creep and shrinkage coefficient, which you can then enter into your element. I have here some predefined models which we can work on. So here you can actually enter the creep and shrinkage and consider them in the relaxation. The tension losses, pre-stress calculates immediate tension losses, as well as I've mentioned, the relaxation for long term. But the immediate tension losses are taken into account into pre-stress, and in the results tab, you will have the tension stress in the tendons after the immediate losses. If we take a look at an example, which I have closed, I have here my pre-stressing force, which I have defined in the beginning. And then the losses can be seen by taking a look at the tension and the tension stress in the tendons. So if I had a 1300 megapascal force stress, I can see the stress in the tendon will, after release, will be 1237. So I have some losses here. This is how you can actually determine the losses in the immediate losses in the tension. For hollow cores, prestress can handle AutoCAD drawings. Let's see, let's open a new model here. I can select my national annex if I want to. Okay, I'll just close the other ones so they don't influence my model right now. So let's see, hollow core 101, give it a length. And I will choose non-standard concrete, hollow cores, and say import. And I can select my files, my AutoCAD drawing. And then I'm prompted with a hollow core section in the drawing. What you need to be aware of, and I want to stress this, is that the drawing needs to be as consistent as possible and as clean as possible. I can see here that I have registered also a small circle, a small contour in the drawing. This is the algorithm looking for closed lines and continuous lines. So it will automatically detect enclosed surfaces and polylines. So you need to make sure that your profile is well defined from the drawing. Also make sure that you have a continuous line and closed regions for the cores in the profile. So I'll just give it a name here. HC 500, 200, let's say. And also need to make sure that the units are according to what I want. I can see the width here, 1.197 meters and 0.2 meters in height. Then I just click import. Let's just give it a different name. So then I could just start using it. So you don't need to define your hollow core section. You're also able to do that. But you can also start using the profile from your AutoCAD drawing. If you have a list of several profiles, you can also import several of them. The topping joint reinforcement, you can define topping in your element and then calculate automatically and design the topping joint reinforcement. You can define topping here. You can add your own by making your own values for your parameters. Let's see if I can just use one for now. Of course, this is not a good example, but I can change it, of course, at any time. Here is a good example. You can calculate the joints automatically, very similar to the way you design the stirrup reinforcement. As I mentioned, you would want to see how the program works on your elements, so please go to StruSoft.com and click on Prestress. Here's where you find all of the information. and features, training videos. That's what I wanted to show you for today. A quick overview of the main features in pre-stress. Now I will switch over to Bogdan and make him a presenter so he can share his screen, and we can see how he uses pre-stress in his project. Okay, Bogdan.
Hello, everyone. Thanks for joining. Right. Hopefully, my screen is now visible to everyone.
Yes, it is. Thanks.
Yeah. Hi. So, thank you for the kind introduction. I'll start with a few words about ourselves. The scope of this intervention today is to talk about our experience with the use of pre-stress, and more broadly, its application in our projects. So we at Gapa Projects are a structural design consultancy. We're based in Bucharest, Romania. We specialize in the design of precast and steel warehouse type structures for storage or production facilities. The majority of the structures that we design are precast concrete frames with cantilever columns and pinned beams and purlins that form the roof structure. The bay dimensions are generally about 12 by 24 meters, with spans occasionally increasing to 32 meters. Most of our projects are based in Romania or the neighboring countries. Those based in Romania also have to satisfy seismic design requirements, as Romania is a seismic country. On these projects, our design scope generally includes all the elements that form the objectives. So this includes the main precast structure, the secondary steel structure supporting the facade and roof, the roof metal sheeting, the ground supported slab, annex structures, and so on. I will shortly browse with you through some of our projects so that we can all get an idea of the type of structures that we're discussing. This Carrefour warehouse was one of our first projects. It's situated close to the capital, close to Bucharest. It covers a surface of about 10,000 square meters. It's a project that we designed in 2017, and it was handed over to the client in 2018. Right next to it, you can see a Decathlon warehouse. Now, we didn't originally design this warehouse, but we are now designing its extension. The extension covers 11,000 square meters. We've actually just delivered the design, and it's now under construction. This was another one of our projects. It's another warehouse for Metro, which is a large retailer here in Romania. The warehouse covers a total surface of 60,000 square meters, is the one with the yellow belt. This was completed in 2019, beginning of 2020. Yeah. It's a large warehouse with several storage facilities ranging from freezer areas, fresh storage for fruit and vegetables, and it also had ambiental storage for non-food items. This entire area that you can see in this photo is one in which, in the development of which we've been heavily involved. The photo is a bit out of date right now. There are several other warehouse units around this, around the ones that you already see. This is a photo from the inside, taken shortly before the handover of the project. You can see the shelving was in process of being installed in the back. This is another project that is dear to us. Corso is one of the main ice cream producing companies in Romania. And in 2018, 2019, they decided to invest in a warehouse unit, again close to Bucharest. This was a special project because the entire storage area was designed for frozen goods. So over the entire lifespan of the structure, it will operate at -25 degrees temperature. Another aspect that is different or special for this project is that it's not the standard box-in-box solution that we see with frozen warehouses, but it's a cold structure solution. So the precast concrete elements are not thermally protected. They will experience sub-zero temperatures for the entire lifespan of this project. This is another unit that we've designed. It's actually a production unit for a non-woven textiles fabricator in Romania. And I include this in all my presentations because I like the colors and the background mostly. So we make sure to always have it. Right, the project that I want to focus on today a bit more is a warehouse that we developed for Daimler. The design was done 2019 and the project was completed in 2020. More than other projects, on this one, there was a very close collaboration with the precast contractor, Somaco, now a member of the Lafarge Group. It's one of the largest precast fabricators in Romania. So on this project, our scope as designers included, again, all the elements. So from the precast structure to the roof sheeting, the services brackets, pretty much every kind of structure there is, primary or secondary. But for this project, we also did the design and the detailing for the fabrication of the precast components. So our drawings went directly to the Somaco factories, and the precast elements were executed following our drawings. And this is one of the projects where prestress was most helpful. In order to complete and deliver our design, we rely on several tools for structural analysis, design, and detailing. We do our modeling entirely in Tekla structures. So we use it both for precast, in situ RC members, and the detailing of the secondary steel structures. On this project, using Tekla structures also allowed us to use a beam approach in our collaboration with the architects and the services engineers. Now, if we focus a bit more on the precast design aspects, we have used prestress on this project for the design of the primary precast beams, the precast purlins, the mezzanine double T elements, so pretty much all precast elements apart from the columns and the column sockets. Before utilizing prestress, we used to have in-house Excel spreadsheets that we would use for the design of these elements. I can quickly browse with you through one of these spreadsheets so you see the type of calculations that we were dealing with. So this is a spreadsheet for one purlin. We start with the input of data. This is just a generic section. Yeah, it's meant to be very versatile for any kind of shape. We're still in the input part. We have now begun the calculations, the tension calculations in the prestress, the tension losses, design checks, SLS cracking with calculations, bending moment diagrams, shear force calculations and diagrams, and so on. So as you can see, it was an extensive spreadsheet. It was a very good tool, and we still use it for quick calculations and I don't know, preliminary design. But this approach had several downsides, for which we decided to also use pre-stress. I'll discuss about these shortly after going through an example with you. Basically, the limitations of the Excel, of the spreadsheet approach have to do with the number of sections that you can do the design in. So all those calculations really only dealt with two sections, the midspan and the support section. So very few intermediate sections were approachable in the Excel spreadsheet. Also, it's impractical to do spreadsheets that cover all these intermediate phases or stages in the life of a precast element. So for these reasons, really pre-stress is irreplaceable to us. Right. I'll return to the presentation. Right. Actually, I've extracted one of the purlins that we've detailed in this project. I extracted it from Tekla Structures into a 3D PDF because I was concerned about the rendering capabilities of this connection. Right. So this is the purlin as we have it in our 3D model. I will make it transparent so we can see the reinforcement inside it. And all these elements have been designed with pre-stress. Right. So what can we see? At the bottom part of the purlin, we have some passive reinforcement. This is how we reinforce beams in Romania. I know that the current practice in some other countries might be a bit different, but I think the principles remain the same. So at the bottom of the purlins, we have passive reinforcement. Then we have pre-tensioned reinforcement, 2 layers of strands in this case. And we have all sorts of other reinforcing elements that we use to do the detailing of the ends of the beams of the purlins. Some of these elements are also characteristic to this recessed end detail. Yeah. We will hopefully cover this shortly. Right, so in section, this is what we see. Let me just do a section through the element. Right. Okay, so here we can see the bottom bars being the passive reinforcement and the pre-stressed strands above it. We have also longitudinal reinforcement at the top of the purlin. Yeah. The links are formed of one wire, and they're bent with machines in the precast factory. Okay. Now, regarding the design of these elements, as you probably know, any pre-stress calculations begins with the definition of the element, the cross-section, geometry, and the span data. I'll just cover things that are supplementary to ones that are easily available to you as beginners with this project. So, as you can see from these snaps, it's possible to model several sections in one pre-stress file. So for example, in this file, we had all the purlins on this project. We had the typical cases with snow drifts, with higher snow loads, and some other sections, that supported some air handling units, so which had some concentrated loads. Also, these sections can be reused from one project to another, so the more the software is used, the easier the process of using it becomes. Right, the definition of the sections is quite intuitive. You'll see when you start using it that it doesn't put any difficulty on the user. You can see in this slide the cross section that we used. As Flavio mentioned previously, we use some debond in the length at the beginning and the ends of the strands. In this case, I had a 1.2 meter debonded length on the second layer, so on these strands here. And you can see that also in the purlin elevation. You can see that they don't start from the beginning, but they start from some distance away from the end. As an observation, the default materials that the program has don't allow you to input bars of diameters that are different to the ones in the database. This was initially an inconvenience for us as Romanian users, because here in our country we use intermediate size bars. So we use 14 millimeter bars or 18 millimeter bars. But we have been able to overcome this issue by defining a new material for the reinforcement, and in this way we unlocked any bar diameter for use. So it's not a limitation. For the shear force design, you can do an automatic design, or you can input a certain link arrangement and check it. This second version is the one that we generally use. On this topic, I would like to point out a setting that I consider very useful. It's found in calculation settings, and it's this shear calculation tab. Yeah, you can see the cotangent of theta is 2.5. Now this parameter can be changed and should be changed when necessary. For example, where we have elements subjected to high levels of shear force, where using such a low angle might yield or might lead to compressive strut failure when it's not necessarily the case. Another situation where we could be obliged to use cotangent of theta of 1 would be if we were doing seismic design. Yeah. Right. After defining the sections and the reinforcement, the design process continues with load combinations, definition, and load input. For each loading situation, a different concrete strength class can be used, thus simulating the concrete hardening process. This is an exercise that would be very laborious without the use of a tool such as prestress. So it was quite difficult for us to do this in Excel and still keep a manageable spreadsheet. Yeah. In this particular case, we decided to add another load combination compared to the default 9 combinations, I believe. The combination number 10 is created by us. It's a ULS short term, as we wanted to investigate whether adding the ULS loads early in the stage of a precast element would lead to more onerous results than adding them towards the end of the lifespan. And this has to do with the fact that early, when the precast element is young, some of the pre-stress force has not vanished through creep and relaxation. So having a larger pre-stress force might actually lead to higher stresses in the compression zone of the purlin. Another useful feature here was already mentioned by Flavio, and it has to do with the long-term parameters. As you can see, you can input the clip coefficient and the shrinkage, the total shrinkage. These values you can determine using the pre-stress, the StruSoft online calculator. The input is quite easy here as well. The age of concrete from casting to present day. This is usually the number of days associated with the lifespan of the element. So 18,250 is roughly 50 years. The concrete strength, it's self-explanatory. The cement type has a very big influence on the overall shrinkage. The relative humidity will also affect these values. The cross-section and the perimeter are self-explanatory. The age of the concrete when loading has started. It depends on what type of element you're looking at. And as with all the checks for these precast elements, it's very important that the designer and the precast fabricator have a good communication, because otherwise we could end up doing a design that is incompatible with the technology or the capabilities of the precast fabricator. Yeah. So it's important for the designer of these pre-stressed elements to understand the production flow, the timing associated with each phase, and other aspects that I'll discuss later on. So yeah, in this case, I consider T0 as the time when the thermal treatment ends. Of course, the thermal treatment doesn't last for 3.8 days; it lasts for hours. But the equivalent age of the concrete when that thermal treatment is completed is 3.8 days. Also, that is the time we consider for the starting of shrinkage. Yeah, so the end of the thermal treatment or the curing of concrete. Now, coming back to what I was saying earlier, it's important to treat the initial phases of precast element's life with care, especially when you're working with a new precast fabricator. Communication is important and helps ensure that the assumptions that we make during the design coincide with the conditions that the elements will encounter during striking, storage, lifting, and transportation. What you can see here is the setting of the support position during the transport stage. You can double click the support and set the distance from the end of the elements. The position of these supports in the design should be chosen with care and communicated through the drawings that we produce by means of sketches or notes on the drawings. But it's important to also consult the fabricator and make sure that what we specify is in line with what he is used to doing, yeah? Or inform him if this is not the case. Right. I've skipped the part of the analysis and the calculation check. It's pretty much straightforward, the way in which we can see the forces in the elements and the output of the design. I wanted to skip to another part that I find interesting. It's the module with the recessed beam design. So apart from the main longitudinal and shear reinforcement in the beam, these bars that we provide towards the ends of the beams are equally important. And the principles behind these calculations can be found in the Precast Concrete Structures book by author Kim Elliott. It's the module is quite intuitive. If you hover over these diameters, then the corresponding bars will be highlighted, so you know which bars these diameters refer to. On the right here, in the result area, are these the shear load on the purlin, and you can see here in the reinforcement section that based on the diameter of the bar that we input, that we pre-select, the program tells us the total required area, and then it determines the number of elements, whether it's longitudinal bars or links and spacing and recommended spacing of these links. Right. If we have just a few more minutes, I would like to also show you another PDF that I've created. Right, let's turn the light on. Okay, so this is a double T element for the mezzanine. This was also designed with pre-stress. A very useful feature in this type of element design is the topping, which you can add or decide not to add if you're doing pre-topping checks. Also, an element to note here is that the thickness of the topping should be introduced with care. Usually these elements have a pre-camber, so the thickness of the topping may not be uniform over the entire length of the element. So the design value needs to be chosen with care. Yeah. Let's see the reinforcement, or better, let's turn off the element, and we can see the bars here. Yeah? We have some lifting hooks inserted in the element, yeah, and we have some forks, we call them, towards the end of the element that serve as anchorage reinforcement for the main longitudinal bars. These red bars will be doing the shear connection between the precast element and the topping concrete. Right. I wish you a very productive use of pre-stress. Please take your time to know the program before using it, and maybe do some examples at the beginning. It's a very powerful, very versatile tool, but as with every design, it requires careful input. Thank you very much for your attention.
Thank you, Bogdan. Thank you for that insightful presentation. It's very interesting to see the design flow of the user and the engineer. Of course, we offer support, and we actually I've spoken to Bogdan many times, and he has questions about pre-stress, and he just calls me or texts me, and he says, hey, how can I use a different diameter, or specific questions about the program. But it's always nice to see this these actual projects put into presented in this way, and see how the brain works, and how the software works, and how they combine the engineering brain and the algorithm from the program. That's always very interesting. So thank you for that. Again, please visit StruSoft.com. You have all the information about our products and our software. Pre-stress has its separate tab, of course. You can see a lot about what we discussed today and more. We have training videos. We offer also one-to-one sessions. If you're new to the program, we can also have a closer look at what you work with and how you can use pre-stress for your project. The easiest way to get started is to click Get Started Now, go to Trial License, and fill out this form. You will then apply and register to receive a trial license and try the software yourself. Thank you everybody for joining. Thank you, Ciprian. Thank you again, Bogdan, for your presentation and input. I wish you all happy designing and a great rest of the day.